To properly ground a 200-amp motor that operates a press, and which is fed by a 480/208-120 volts transformer with a backfeed configuration, there are specific steps and materials required to ensure safety and compliance with electrical codes. The necessary materials include a grounding conductor rated for 200 amps, a ground rod or plate, ground clamps, and a multimeter. The process involves several key steps. Firstly, determine the grounding point. The grounding point should be a cold water pipe, a metal structure, or a driven ground rod or plate. It is crucial to ensure that the chosen grounding point has a low resistance to earth, facilitating effective dissipation of fault currents. Secondly, install the grounding rod or plate if necessary. If a suitable grounding point does not already exist, drive a 6-foot ground rod into the earth. To improve grounding effectiveness, connect a grounding plate to the top of the rod. Thirdly, connect the grounding conductor to the grounding point. Attach one end of the 200-amp grounding conductor to the grounding point using a ground clamp. Ensure the connection is secure and corrosion resistant to maintain a reliable ground path. Fourthly, connect the grounding conductor to the motor. Connect the other end of the grounding conductor to the motor's grounding terminal. This terminal is typically marked with a green or green and yellow color to indicate its purpose. Fifthly, test the ground resistance. Using a multimeter set to the ohms setting, measure the resistance between the grounding conductor and the grounding point. The resistance should ideally be less than 1 ohm. A low resistance value confirms that the grounding system can effectively conduct fault currents to ground. Sixthly, verify proper polarity. Confirm that the polarity of the transformer connections is correct. The secondary, which is 480 volts, should be connected to the motor, while the primary, the 480/208-120 volts side, should be connected to the backfeed power source. Proper polarity is essential for the correct operation of the transformer and the motor. There are several additional considerations to keep in mind. The grounding conductor should be sized in accordance with Article 250(66) of the National Electrical Code. This ensures that the conductor is capable of safely carrying fault currents. The grounding system should be inspected and tested regularly to ensure its integrity. Regular inspections can identify any issues such as corrosion, loose connections, or physical damage that could compromise the effectiveness of the grounding system. Avoid using sharp bends or kinks in the grounding conductor. Sharp bends can increase the impedance of the conductor, reducing its effectiveness. If the transformer is located outside, use a weatherproof grounding enclosure to protect the connections from the element. This enclosure should be rated for outdoor use and provide protection against moisture, corrosion, and physical damage. The absence of a neutral on the secondary side of the transformer does not affect the grounding requirements for the motor. The grounding requirements are primarily focused on providing a safe path for fault currents, regardless of the presence of a neutral conductor. Proper grounding is essential for safety and to protect the equipment from electrical hazards. A properly grounded system minimizes the risk of electric shock and reduces the likelihood of equipment damage due to electrical faults. For further clarification, consider the following points about grounding systems. Grounding ensures that non-current carrying metal parts of equipment are at ground potential, minimizing the risk of electric shock. Grounding provides a low impedance path for fault current to return to the source, allowing overcurrent protection devices to quickly trip and clear the fault. Bonding connects non-current carrying metal parts to create an electrically conductive path, ensuring that all parts are at the same potential. The size of the grounding conductor is determined by the size of the overcurrent protection device protecting the circuit. Ground rods should be driven deep enough to reach moist soil, typically at least 8 feet. The resistance of the grounding system should be tested regularly, and any necessary corrections should be made to ensure it remains effective. Ground fault circuit interrupters, or GFCIs, provide additional protection by detecting small imbalances in current and quickly tripping the circuit. Surge protective devices, or SPDs, protect equipment from voltage surges caused by lightning or other electrical disturbances. Regular inspection and maintenance of the grounding system are essential to ensure its continued effectiveness. This includes checking for corrosion, loose connections, and physical damage. Always follow the manufacturer's instructions and applicable electrical codes when installing and maintaining grounding systems. If you are not qualified to perform electrical work, consult a licensed electrician. Grounding systems play a critical role in electrical safety, protecting people and equipment from the hazards of electrical shock and equipment damage. The National Electrical Code provides detailed requirements for grounding and bonding to ensure safe and effective electrical systems. Always consult the latest edition of the NEC and other applicable codes and standards when designing, installing, and maintaining grounding systems. By understanding the principles of grounding and following best practices, you can create a safe and reliable electrical system. For a 200 amp motor, additional details on grounding include selecting the correct size of the grounding electrode conductor. According to NEC Table 250.122, the size of the grounding conductor depends on the size of the overcurrent protective device. For a 200 amp circuit, a copper grounding electrode conductor should be at least number 6 AWG copper. If using aluminum, it should be number 4 AWG. Selecting the right type of grounding electrode is also critical. Common grounding electrodes include ground rods, ground plates, and metal water pipes. A ground rod should be at least 8 feet long and driven into the ground vertically. A ground plate should have a surface area of at least 2 square feet. If using a metal water pipe as a grounding electrode, it must be in direct contact with the earth for at least 10 feet. The grounding electrode conductor must be securely connected to the grounding electrode using approved methods such as exothermic welding, listed connectors, or bolted connections. The location of the grounding electrode is important. It should be located as close as practical to the equipment being grounded and should be protected from physical damage. The grounding electrode system should have a low impedance path to ground to ensure that fault currents can quickly and safely return to the source. Regular testing of the grounding system is essential to ensure that it is functioning properly. The resistance to ground should be measured using a ground resistance tester. The NEC requires that the resistance to ground should not exceed 25 ohms. If the resistance is higher than 25 ohms, additional grounding electrodes may be required. Grounding and bonding are essential for electrical safety, and it is important to follow all applicable codes and standards when installing and maintaining grounding systems. Proper grounding provides a low impedance path for fault current to return to the source, allowing overcurrent protection devices to quickly trip and clear the fault. Bonding connects non-current carrying metal parts to create an electrically conductive path, ensuring that all parts are at the same potential. The size of the grounding conductor is determined by the size of the overcurrent protection device protecting the circuit. Ground rods should be driven deep enough to reach moist soil, typically at least 8 feet. The resistance of the grounding system should be tested regularly, and any necessary corrections should be made to ensure it remains effective. Ground fault circuit interrupters, or GFCIs, provide additional protection by detecting small imbalances in current and quickly tripping the circuit. Surge protective devices, or SPDs, protect equipment from voltage surges caused by lightning or other electrical disturbances. Regular inspection and maintenance of the grounding system are essential to ensure its continued effectiveness. This includes checking for corrosion, loose connections, and physical damage. Always follow the manufacturer's instructions and applicable electrical codes when installing and maintaining grounding systems. If you are not qualified to perform electrical work, consult a licensed electrician. Grounding systems play a critical role in electrical safety, protecting people and equipment from the hazards of electrical shock and equipment damage. The National Electrical Code provides detailed requirements for grounding and bonding to ensure safe and effective electrical systems. Always consult the latest edition of the NEC and other applicable codes and standards when designing, installing, and maintaining grounding systems. By understanding the principles of grounding and following best practices, you can create a safe and reliable electrical system. Also consider supplemental grounding when there is a backfed transformer involved. Supplemental grounding electrodes are additional grounding electrodes installed to improve the overall grounding system. Supplemental electrodes can be used to reduce the resistance to ground and provide a more robust grounding system. Common types of supplemental grounding electrodes include ground rods, ground plates, and ground grids. Ground rods are the most common type of supplemental grounding electrode. They are typically driven into the ground vertically and are connected to the grounding system with a grounding conductor. Ground plates are metal plates that are buried in the ground and connected to the grounding system. Ground grids are interconnected grids of grounding conductors that are buried in the ground and connected to the grounding system. Supplemental grounding electrodes should be installed in accordance with the NEC. The NEC provides specific requirements for the number, spacing, and installation of supplemental grounding electrodes. The number of supplemental grounding electrodes required depends on the soil resistivity and the desired resistance to ground. The spacing of supplemental grounding electrodes should be at least the length of the grounding electrode. For example, if using an 8-foot ground rod, the ground rods should be spaced at least 8 feet apart. Supplemental grounding electrodes should be installed in locations where they will be effective, such as in areas with moist soil. Supplemental grounding electrodes should be properly connected to the grounding system. The grounding conductor should be sized according to NEC Table 250.122. Supplemental grounding electrodes can improve the performance of the grounding system and provide additional protection against electrical shock and equipment damage. They are particularly useful in areas with high soil resistivity or where a low resistance to ground is required. In addition to the NEC, other standards and guidelines may apply to supplemental grounding electrodes, such as those from the IEE and UL. These standards provide additional information on the design, installation, and testing of supplemental grounding systems. Always consult with a qualified electrical engineer or electrician before installing supplemental grounding electrodes. A qualified professional can help ensure that the supplemental grounding system is properly designed and installed in accordance with all applicable codes and standards. Another aspect is to also consider equipment grounding conductors. Equipment grounding conductors, or EGs, are used to connect the non-current carrying metal parts of equipment to the grounding system. This provides a low impedance path for fault current to return to the source, allowing overcurrent protection devices to quickly trip and clear the faults. EGC are required by the NEC for most electrical equipment. The size of the EGC is determined by the size of the overcurrent protection device protecting the circuit. EGC can be either copper or aluminum. Copper EGC are more common than aluminum EGC, but aluminum EGC can be used if they are properly sized and installed. EGC must be installed in the same raceway or cable as the circuit conductors. This ensures that the EGC will be able to carry fault current back to the source quickly and efficiently. EGC must be securely connected to the equipment and to the grounding system. This can be done using a variety of methods such as screws, bolts, or listed connectors. EGC must be protected from physical damage. This can be done by installing them in a raceway or cable that is designed to protect them from damage. EGC play a critical role in electrical safety. By providing a low impedance path for fault current to return to the source, they help to protect people and equipment from electrical shock and equipment damage. Regular inspection and maintenance of EGC are essential to ensure their continued effectiveness. This includes checking for corrosion, loose connections, and physical damage. If an EGC is damaged, it should be repaired or replaced immediately. Always follow the manufacturer's instructions and applicable electrical codes when installing and maintaining EGC. If you are not qualified to perform electrical work, consult a licensed electrician. The material of the grounding wire also matters, and copper is a better choice. Copper grounding wires offer several advantages over aluminum grounding wires, including higher conductivity, better corrosion resistance, and greater strength. Copper has a higher conductivity than aluminum, which means that it can carry more current for a given size. This is important for grounding wires because they need to be able to carry fault current back to the source quickly and efficiently. Copper is also more resistant to corrosion than aluminum. This is important because grounding wires are often exposed to moisture and other corrosive elements. Copper is also stronger than aluminum, which means that it is less likely to break or become damaged. For these reasons, copper grounding wires are generally preferred over aluminum grounding wires. However, aluminum grounding wires can be used if they are properly sized and installed. Aluminum grounding wires must be larger than copper grounding wires to carry the same amount of current. Aluminum grounding wires must also be protected from corrosion. Aluminum grounding wires should only be installed by qualified electricians who are familiar with proper installation techniques. The type of soil also matters, as highly resistive soil requires special consideration. High soil resistivity can significantly impact the effectiveness of a grounding system. Soil resistivity is a measure of how well soil conducts electricity. Soils with high resistivity are poor conductors of electricity, which can make it difficult to establish a low impedance path to ground. In areas with high soil resistivity, special measures may be necessary to improve the performance of the grounding system. One common technique is to use multiple ground rods connected in parallel. This helps to reduce the overall resistance to ground. Another technique is to use chemical ground rods. Chemical ground rods are filled with chemicals that help to improve the conductivity of the soil. In extreme cases, it may be necessary to use a ground grid. A ground grid is a network of interconnected conductors that are buried in the ground. Ground grids provide a large surface area for current to flow into the earth, which can significantly reduce the resistance to ground. Soil resistivity can vary significantly depending on the type of soil, the moisture content, and the temperature. It is important to measure the soil resistivity before designing a grounding system. This can be done using a soil resistivity meter. If the soil resistivity is high, special measures may be necessary to improve the performance of the grounding system. Consulting with a qualified electrical engineer or electrician is recommended to ensure that the grounding system is properly designed and installed.